We're now ready to define the concept of a basis, this pillaring set, the set that includes the pillars of our subspace. So a set B consisting of vectors v1, v2, vn, consisting of n vectors, and let's say that this set is actually spans a vector space S of dimension n, is called a basis for S. Okay, that sounds confusing, doesn't it? Okay, so let me rephrase it in a different way. This is one formal definition. I can give you several more. I'm going to give you a different description of it in different words. So let's say that we have a vector space S, and we know that this vector space has dimension n. Then if we can construct a set of n vectors, exactly n, the same as the dimension of the space, and this set actually spans the whole vector space, then we're going to say that this set is a basis for our vector space. So this is a minimal set. It's the smallest one. Remember, because S has dimension n, I cannot get any smaller set of vectors that span it, but this particular one spans the whole thing. So we have enough vectors and this spans everything, and we don't have too many vectors, so we have just the amount of vectors. Then we call it a basis for S. Okay? So for example, ijk, well, is a basis for R3, isn't it? Because by using I, J, and K, we can span all of R3, and R3 has dimension 3, and therefore it's a basis. So it's a fairly good starting analogy or a starting example. In fact, this one is called the standard basis for R3. Okay? It's the usual one, the one that we have been used to and that we're going to use unless we have some good reasons for not using it. Another example, if I look at a set of polynomials 1x and x squared, is also basis for P2, the set of all polynomials of degree at most 2, right? I can construct any such polynomial by using those three, and I need to use all three of them, otherwise I'm going to miss some polynomials. For instance, if I drop x, I can never get a polynomial which has an x in it. Only polynomials that have a constant and an x squared, and the same for the other two. So that means that P2 is set of them. It's a space of dimension 3, and these are three vectors, span all of it, so it's a basis. Notice how these two concepts of basis and dimension are really linked. Sometimes one feels like, wait a minute, which comes first, the chicken or the egg? Well, they come together in a way, right? So we should take them as a pair, and that's another way to do it. Just define them together. Now, one consequence of this definition is that any basis has to be made up of an independent set. Okay, so, or another way to say that the vectors that are part of a basis form an independent set, or independent of each other. You want the proof for that? Well, it's very easy. Okay, let's assume that we have a basis, and the basis forms a dependent set. Well, if it forms a dependent set, remember, one of the consequences of being a dependent set, it means that there is at least one of the vectors in the set is a linear combination of the others. But if it's a linear combination of the others, why do we need it? We can throw it away and still end up with the spanning set. Okay? So the proof is quite simple, simply that if bases were not independent, so if it were dependent, then one of the vectors could be eliminated, which would give us a smaller basis, which is a contradiction to the very idea of a basis.